Okay, so today we'll be looking at optimization problems. With constraints. In single variable calculus, you use the problems of the form. For example, find the area, find the maximum area or minimum area of a, let's say, rectangle given that its perimeter is 30 centimeters, right? So in this last part here, given that its perimeter is 30 centimeters, this is what is known as a constraint. Let's translate this problem into numbers, right? So you have a rectangle here of dimension x and y, so the area is equal to x and y. Now this is a function of two variables. Now the constraint is that x plus y equals 30, right? And because of the constraint, you have y equals 30 minus x, and because of the constraint, the area becomes a function of x only as opposed to a function of x and y. So the area becomes 30x minus x squared. So you can find the maximum of this area, not the minimum, right? So this is a quadratic function that looks like this, right? So this is the area with x. This is 0, this is 30, and this is, so the area is maximized. So the area is maximized when x equals 15. This is in the value of 0 and 30, and of course that would make this equal to 450 minus 225, which is as area max would be 225. All right, so and of course the minimum area would be 0. At x equals 0 and x equals area minimum is of course 0. X equals 0 and x equals 30, right? So this is where meaning that's where this collapses to a line or to this, right? One dimension becomes 0. If x equals 0, y equals 30, and if x equals 30, then y equals 0. Okay, so what we're going to do is we're going to look at these optimization problems, similar optimization problems, but in multivariable calculus, right? Okay, so, and we're going to use a method, the method of Lagrange multipliers. Lagrange multipliers. Alright, so before that, what we have to do is we have to get used to the concept of level curves. And level surfaces. What is a level curve? So imagine you're given a surface with relation z equals f of xy. Now if you replace this z by a constant, I don't know, f xy equals some constant c, you get a curve on the xy plane. xy plane, right? And that curve indicates the height of the surface. So let's say you have a sphere, right? That looks like a unit sphere, right? The unit sphere has equation z equals has two equations, in fact. There's two functions, 1 minus x square minus y square, and z equals negative 1 minus x square minus y square, right? So the combination of these two functions, combination of these two guys functions gives you a unit sphere, right? Now let's take z to be some constant, right? So for in the first function, if I let's say z equals k, right? Then k equals, so this is my fxy. This is one surface, this is another surface. Remember, a sphere is basically, in mathematical terms, it's basically two hemispheres, right? Joined at the center. And this is, let's call this g of xy. They're obviously not the same function. So, if f of xy equals k, then k equals 1 minus x square minus y square. Or, you have k square equals 1 minus x square minus y square. So x square minus x square plus y square, right? This is equal to 1 minus k square. Now, when k equals 0, right? Now, what are the when k equals 0, this becomes x squared plus y squared equals 1. This is a unit circle centered at the origin. And notice that all this equation gives you a circle of radius square root of 1 minus k square, where of course k can be 0 and k can be 1. So this is the restriction on k. Now let's draw the just draw our level curves, right? So for example, sorry about that, that's not a circle. So now this is circle, they should be concentric circles actually, right? Sorry, okay, 2 is enough, I guess. This is k equals 0. We have the circle x squared plus y square equals 1. And if k is equal to 1, we have the point at the origin. Let this be some intermediate value. Let k be, 0.5. Then this becomes x squared plus y square. K equals 0.5. Then you have x squared plus y square equals 3 over 4. So we have a circle of radius root 3 over 2. So these guys, these circles, the level circles are the level curves of the sphere x squared plus y squared plus z squared equals 1. Right, so these guys are level. These are the level curves of the sphere. Now, of course, there are level curves for any so there are infinitely many level curves, right? For each value of k, you have a curve. You could talk about the level curves of any surface. For example, if you have a f of xy equals x squared plus y squared, right? So this is a this should give you a cone, right? Because at each level you have a if for each value of z, right? So this is z equals x squared plus y squared. This gives you a cone because when x equals 0, y equals 0, you have z equals 0. So at the origin you have the tip of the cone, and the cone expands as you go up. Right. So in fact, it gives you a double cone. It's a double cone because x and no, it doesn't give you a double. Sorry, it gives you a single cone. It goes up, right? So the cone kind of looks like this. I'll show you. This is your cone. Of course, at the origin, so you set axis, y-axis, x-axis, z, y, x. Right. So this is z equals x squared plus y squared, and the level curves of this are given by, of course, f x y equals some constant c, and if x squared plus y squared, and of course c is greater than 0 and greater than or equal to 0 equals c, then we have a circles of radius square root of c, right? Centered at the origin, centered. So you could draw level curves for just about anything, for any surface. Right, now let's try to put our knowledge of level curves to use here. We want to solve a problem, and the problem is optimization with a constraint. So let's say we want to maximize, or let's say we want to maximize a sort of particular function. Call it f of xy. Right. For now, let's say our function has just two variables, x and y. I want to maximize it subject to some constraint. Let's call that constraint g of xy equals k. Okay, so we draw our level curves. Sorry. So these are our axes, right? Y, x, and we have these level curves. F of xy equals 1, f of xy equals 2, f of xy is equal to 3. These are level curves of f, right? And we want to f of xy equals 4. So f, if I doesn't have any maxima or minima, it's just goes on and on to infinity. Now I want to place the condition g of xy equals k. And notice that this also has a form of a level curve. This is a level curve. So let's draw this level curve here. So let's say this looks like this. This is the level curve, g of xy equals k. Notice that this level curve just touches f of xy is equal to 3. Right? Just touches f of xy is equal to 3. In other words, g of xy equals k is just tangent to f of xy is equal to 3. xy is equal to k is tangent to f of xy is equal to 3. Right? In that case, what happens in that case? In that case, we know for a fact that they share a common tangent vector. Right? Okay, g of xy is tangent to f of xy is equal to 3, but it doesn't go any further, right? It doesn't go until f of xy is equal to 4 or 5. It just stops at f of xy is equal to 3. It doesn't go beyond 3. So we know that g of xy equals k and f of xy is equal to 3 share a common tangent vector, right? They share a common tangent vector. We know from the diagram that given the constraint g of xy is equal to k, given the constraint g of xy equals k, f of xy has a maximum value of 3 given this constraint. Now the mathematical way of expressing this is to say that both level curves have the same tangent. Now if they have the same tangent, then we also expect them to have the same normal vector, right? If they have the same tangent vector, we also expect them to have the same normal vector. And remember that the normal vector to any curve the normal vector to any curve is parallel to the gradient vector, because the gradient vector is perpendicular to the tangent vector. If you recall, in 2 dimensions, RT is given by XT and YT, right? This is a curve in 2 dimensions. In that case, R prime T, which is a tangent vector, is of course given by dx over dt, comma, dy over dt. Now, if the curve is given by f of xy is equal to some constant, then of course, and x is some function of t and y is some other function of t, then df over dt is 0. But df over dt may also be written as partial f partial x times dx over dt plus partial f partial y dy over dt, where this is basically equal to this vector, partial f partial y, dot this vector, dy over dt. This guy is basically del f, and this guy is r prime t. Now, of course, this is equal to 0. So this tells me that the gradient is perpendicular to the tangent vector. So now, if two curves share the same tangent vector, then they must also share the same. If two curves share the same tangent vector at a point, then they must share the same gradient vector. They must have parallel gradient vectors, not the same gradient vector. They must be parallel. If two curves share the same tangent vector, then their gradient vectors must also be parallel, right? Now, f and g, they share the same tangent vector, so that tells me that the gradient vectors of f and g, the gradient vectors, sorry, not f and g, the curves, right, of f xy equals 3 and g xy equals k are parallel. So this tells me that they're, when they touch, touch, we have del f x y. So let's say they touch at the point x naught y naught. At x naught y naught equals some constant number, some constant lambda times del g x naught y naught. So if I could solve these equations, right? If I could solve so this basically gives me two equations, right? So this is basically two equations, right? So this is basically fx at x naught y naught equals lambda gx at x naught y naught, and I have f of y at x naught y naught equal lambda g sub y at x naught y naught, and I have another constraint, and I have the constraint, of course, so g of x naught y naught equals k, right? So I have three equations. Of course, k is known. Equations, three variables, x naught, y naught, and k. Right? So I could find where f is maximum or minimum using these three equations, and of course, and in the process find lambda. So not x naught y naught k, x naught y naught and lambda. So in the process, I could find I could use these three equations to find x naught, y naught, and lambda. So we want to find x naught and y naught and plug that into f just to find the maximum or minimum value of f. Now let's try to give this intuition of ours. So all of this was intuition, right? So let's try to give it some precision. So let's say we have a function f, which is with an extreme value at p, right? Function f with an extreme value at P, x naught, y naught, z naught, right? And of course the surface, the function f is a function of three variables, right? Function of three variables, meaning it takes you from R3 to R. Right now, let's say I want to find the extreme value of this subject to okay, let's think about this way. So then a curve with vector equation, and so let's C be a curve, right? So let's C be a curve on this surface. So this is your function f. This is the surface S, right? So which is f of x given by y z equals some constant, and we have a curve on this surface, right? Let's call that curve C, and it's given by r. The vector equation is given by r x y z, right? And we want our and we want to find and we have the, and we're given a constraint g of x y z equals some constant, right? Some constant, and want to find the extreme values of the function f on the surface. Now consider the composite function. Right? Consider the following composite function. Consider the following composite function. F of xt, yt, zt, right? Now notice something here. Notice that f of xt, yt, zt, right, is going to give me, is going to be on this curve C, right? Because this is the composition of the surface and the curve. So this guy is essentially a function of t, right? So in order to maximize this, function, what do I have to do? I have to set, in order to extremize this function, not to maximize, but to extremize this function, I have to set df by dt equal to 0. Now what happens if I set df over dt equal to 0? See what I get. I get partial f over partial x times dx over dt plus partial f over partial y times dy over dt plus partial f over partial z times dz over dt equals 0. Or in other words, del f dot r prime t equals 0. Now, what this tells me is that the gradient vector del f is orthogonal to the tangent vector to every curve C. But given the constraint, right? So we also have a constraint g of x, y, z. Now g of x, y, z is orthogonal to r prime t, right? So remember, r prime t is a curve that passes through both surfaces, fxyz equals c and gxyz equals some other constant. All right. So sorry, rt is I'm sorry, r x naught, y naught, z naught, right? This point, right, y naught, z naught, is on both the surface S given by this, and let's say call the surface T given by z equals k, right? So this tells. So I also know for a fact that delta g dot r prime t naught equals 0. How do I know this? Well, I know this because since that curve is on G, since that point is on G, I expect G to be del G to be perpendicular to the tangent at that point. So del G dot r prime t naught equals 0. In that case, I know for a fact that del f and del G are parallel, right? Or in other words, del f at x naught, y naught, z naught equals lambda del G at x naught, y naught, z naught. And this gives us the method of Lagrange multipliers. Right, so the method of Lagrange multipliers is that you're given a function, right, and you're given a constraint for the function, right? You call that constraint G. Now, if the constraint is G, then this equation, right, delta f equals lambda del G, this gives you, this is essentially, it's a vector equation gives you 3 equations in 3 dimensions, right? And the constraint G x y z equals k, this is another equation. So in total you have 4 equations. You have 4 variables to find: lambda, x, y, and z. So the 4 equations are fx equals lambda gx, fy equals lambda gy, and fz equals lambda gz, and this is of course the 4th equation. Okay, so let's do example 1 from our let's do the two examples from the book, right? And okay, so and then we'll move on to 2 constraints. Okay, so the first example tells you that gives an find extreme values of the functions x squared plus 2y squared on the circle x squared plus y squared equals 1. F of x, y equals, okay. So we're given a function of 2 variables, right? Given, and we're given a constraint. So our gxy constraint equals 1. So gxy equals x squared plus y squared. Now let's set up our equation, right? So we are supposed to find x squared plus 2xy. So fxy, this is example 1, page 1024 and page 1022 and 1023, so 1021, yeah, 1021 and 1022. Right, so fxy equals x squared plus 2y squared. Gxy equals x square gxy equals x square plus y square, and we want to set gxy equals 1. So now let's see what happens here. So remember, we have three equations. We have four. So here, since we're dealing with two variables, we have three equations. Right. So first equation is fx equals lambda gx. Second equation is fy equals lambda gy, and third equation is g of xy equals 1. Right. So we want to optimize fxy. We want to find either the minimum or the maximum, something, right, given this constraint. Now let's try so let's try solving these equations, right? So first equation, we would have fx, of course, would be twice x, and equals lambda gx, which is equal to lambda twice x, right? And fy equals lambda gy, you would have 4y equals lambda times 2y, and of course this is x squared plus y squared equals 1. Right, so you would have to solve these equations. Now notice something here, that I could cancel out x and I could cancel out x and y, where notice something here is that what I notice here is that x and y cannot both be 0. Why? Because x squared plus y squared equals 1. So how do we solve this then? So let's look at this equation. Right? Don't divide by x, okay? Because x could don't divide by x or y. One of them could be 0, but both cannot be 0, but one of them could be 0. But one of them could be 0. Right, so let's see what happens. So the first equation, 2x lambda, it gives me 2x, 1 minus lambda equals 0, or lambda equal, so which tells me that lambda equals 1, or x equals 0. Now if lambda equals 1, then 2y, then of course y equals 0, right? If lambda equals 1, then y equals 0. And this tells me that x equals plus or minus 1, right, from here. So we have plus minus 1, 0 as one of our critical points. Right? Now what happens if x equals 0? If lambda is not equal to minus 1, what happens if x equals 0? So if x equals 0, well in that case y could be equal to, if x equals 0, then y is equal to y equals plus or minus 1, right? So we found another critical point, 0 plus or minus 1. And yeah, and so if y equals plus or minus 1, so you have plus minus 4 equals lambda plus minus 2, so lambda equals to 2. I mean, it's not really necessary to find lambda out, but that's what it equals. Okay, so we found four critical points, right? 1 0 minus 1 0, 4 critical points. 1 0 minus 1 0, 0 1, and 0 minus 1. Right? Now, if you have 4 critical points, you want to examine what happens to f at these 4 critical points. What is f10 equal to? Remember, f is given by x squared plus 2y squared. So f10 is 1. So f of xy equals x squared plus 2y squared. So f10 is 1. f01 equals 2. In fact, f plus minus 1 0, both of these are 1 and both of these are 2. Right? So we found our maximum at 1 0 as plus minus 0 1. These are points of maxima, and the 1 0, these are points of minima. Right? These are minimum points. So now notice what happens if I if we take C. Let's look at this diagram here. Right. So this was a constraint: x squared plus y squared equals 1. Right. And this is a paraboloid. X squared plus 2y squared. Right, so if I take z equals x squared plus 2 instead of y, right, 1 minus x squared, this becomes 2 minus x squared. So directly above the paraboloid here, I have my I have this curve C in 3 dimensions, and the projection of this curve C is x squared plus y squared equals 1. And the highest point of C is 2, and the lowest point of C is 1. Now notice what happens if I differentiate this. dz over dx equals negative twice x. So set x equals 0. I get z of 0 is equal to 2, right? And that's basically my that's basically where the highest point, right? And if I set and z of 1 is equal to 1, right? Because the maximum value of x can be 1, right? So because we're on the circle, so x squared plus y squared equals 1. So x squared cannot be greater than 1. So x cannot be greater than 1. So setting x equals 1 gives me 1. So which are of course my maximum and minimum values. Okay, so now you have a more practical problem in 3 dimensions, and you will. And the way to do this is analogously to find the gradients of the constraint and of the given function. So let's see what the problem says before we do it. So let's look at what the problem says. We want to find the extreme value for the volume of a box. So we have the area of cardboard, right, given. The area of cardboard given equals 12 square meters, and the volume has to be maximized, right? So the volume is x, y, z, and this is the constraint. Right now, we set up Lagrange's equation. So area, of course, is, since it's a cubic box, right? This is given with two. In fact, we should draw a diagram for the box. Draw a line. So one rectangle. Right, you have another rectangle. Just join the rectangles. Right, and x, y, z. I mean, the area of the box is, of course, then 2xy plus 2xz plus 2yz. This is equal to 12, or xy plus xz plus yz equals 6, right? And given this constraint, we want to maximize this guy. Now, constraint del v equals lambda del a. So del v is, of course, given by yz, xz, xy, and this is, of course, equal to lambda del a. So y plus z, x plus y, or x plus z, and then you have x plus y. Cool. So our constraint equations are, Lagrange multiplier equations are yz equals lambda y plus z, xz equals lambda x plus z, and xy equals lambda x plus y. These are three simultaneous equations that we have to deal with, and we have the constraint equation, which is xy plus yz plus xz equals 6, not 12, 6. Alright, so these are the four equations that we have to look at, that we have to solve. We have to solve for x, y, z, and lambda. Alright, so this is equation 1, this is equation 2, this is equation 3, this is equation 4. Of course, there's no general method for solving these equations. One way you could do this is as suggested by the book. You multiply both sides by you multiply this by x, right? If you multiply this by x, equation 1 by x, equation 2 by y, equation 3 by z, then they're all identical. Then they all become identical. So let's follow the book's method for solving these equations, right? So you would have xyz equals lambda xy plus xz. You would have xyz equals lambda xy plus zy, and of course you'd have oh wait, just a minute, I think I made a mistake somewhere here. There should be 2z, yz should actually be 2z plus y. 2z plus y. Because you have because a constraint is given in terms of twice x, twice y, and twice z, right? So 2z plus y, and this should be just a moment. Actually, just give me a moment. Oh, sorry. The constraint in the book's example is not 2xy plus 2yz plus 2y. This is not the constraint. The constraint has a missing yz. Right. So this is the constraint. So we're not allowed to divide by. We're not allowed to divide by 2 just to get rid of the 6. Right. So forget about the box. Right. Forget about the box. I thought it'd be 2xy plus 2y. Forget about the box. Right. The constraint is as given, right? I thought it was a typo in the book. No, it's not a typo. This is 2xy plus 2yz plus xy equals 12. Right? So this is the constraint. This is the constraint. This is my constraint. So the constraint equation is basically 2xy plus 2yz plus xy equals to 12. And if you so this becomes 2. Okay, so if you find a derivative with respect to x, this becomes of course this is xz, right? And this is xz, and so let's see what happens if you sorry, this is not xz, this is xy. To xz, this is the constraint. Making a mess of this question. 2xz plus 2yz plus xy equals 12. So 2xz plus 2yz plus xy equals 12. In that case, if you so this is not an area constraint, right? This is not an area constraint. This is just a constraint on the given the variables, right? Let's call this constraint g of xy. Right? Let's call this constraint g of xy. Sorry, g of xy z equals some constant, right? G of xyz equals some constant, right? And this is a general constraint. This is not an area constraint. So del g of xyz equals this should equal twice z plus y, comma, and then you have twice z plus x, comma, and twice x plus twice y, right? So twice z plus y, twice z plus x plus twice y. So y plus twice z, x plus xy should equal 2 lambda x plus y, right? And this equals x plus twice z. Let's see if I've gotten the constraints right this time around. Twice z plus y, yz equals twice z plus y, right? Xz equals x plus twice z, and xy equals twice x plus twice y, lambda, right? And of course the constraint equation is twice xz plus twice yz plus xy equals 12. Now this makes sense, right? So you multiply everything by, so you want to make the right hand side in each want to make the LHS in each equation equal to xyz. So you multiply this by x, you get lambda xy plus 2xz, right? Multiply this by y, you get lambda xy plus 2yz, and you multiply this by z, third equation by z, you get lambda 2 lambda xz plus yz. Alright, okay, so we want, the reason we did this is we want to make these three guys equal, right? And of course you have, if these two guys are equal, then what do you get? You get lambda xy. So lambda xy, they cancel on both sides. So you're left with lambda xz equals lambda yz. Lambda xz equals lambda yz. Now, we don't want lambda to be 0, right? If lambda equals 0, what happens if lambda equals 0? Well, lambda equals 0, we would have yz equals 0, xz equals 0, and xy equals 0, right? And what would that do? That would force us to set, I mean, x, y, and z equal to 0, and which would be, and the dimensions of the box then would all be equal to 0, and that wouldn't make any sense, right? So the best we could, and of course z is not equal to 0, lambda is not equal to 0, so we know that x equals y. Now if x equals y, then of course this third equation becomes, okay, let's see what we can derive from these last two equations, right? So we have lambda xy plus 2yz equals twice lambda xz plus yz. Now, of course, you can cancel the lambdas since they're not equal to 0. So xy equals xy xy minus 2xz equals 2y. So there's a 2yz here and there's a 2yz here, so these guys cancel. Take x out, y minus twice z, right, equals 0. So this tells you that y equals twice z. Right, so we have y equals x and y equals twice z. Let's plug that into the constraint equation. 2xz, what was the constraint equation? 2xz plus 2yz plus xy equals 12. Plus xy equals 12. Oh, this is the area of a box without a lid, right? So that's why it's missing a 2 here, right? So if it did have a lid, then you'd have a twice xy, right? So this is 1 xy actually. Okay, so 2xz. So instead of okay, so let's replace. Let's write everything in terms of y, right? So you have 2x times half. Okay, so instead of twice x, you may write twice x. You may write twice y, and instead of z, you may write half y, right? So you have twice y dot half y, twice y dot instead of z, of course, it's half y, and instead of x, again, you may write y plus y squared equals 12. So you end up with 3y squared equals 4 or y equals 2. Remember, y cannot be minus 2 because it's a because y is the dimension, y is a dimension of a box, right? And if y equals 2, then x equals 2 and z equals 1, right? Now this tells me that the maximum, that the volume is 2 to 1, which is equal to 4, right? 4 cubic meters. Okay, so we have another example. We want to find the which is example 3 on page okay, we have exactly 2 more examples. Example 3, which is to find the points on a sphere which are closest and farthest from the point 3, 1, minus 1. I expect, please go through this example. And the fourth example is that you are to find the extreme values of a particular function on a disk, right? On a disk D. So for that, if you remember from our previous lecture, if you are to find the extreme values on a disk, you have to first, so let's look at example 4, pages 1025, 1024 and 1025. Extreme values on a disk. Extreme values on a disk. Alright, now if we are to find extreme values on so we have the disk is given by x square plus y square is less than or equal to 1, right? And x square plus 2y square is equal to, and we're and our function is f of xy equals x square plus 2y square. Now if you recall from the previous lecture on critical values, in order to find extreme values on a disk, you find the extreme values in order to find extreme values on a domain, you find extreme values on the boundaries of the domain, and you find extreme values inside the domain, and then you compare. So what are the extreme values on the boundaries? Well, you have the boundary is x square plus y square is equal to 1, and we found the extreme values on the boundary, right? They were equal to 2 and 1, I think. Yeah, 2 and 1. So the extreme values on the boundary, are 2 maximum and 1 minimum. What about the extreme values inside the disk, right? Well, inside the disk, what we can do is we could find, using our previous methods, inside the disk. Well, this is twice x, and fy of xy is equal to 4y. So inside the disk you have x equals 0, y equals 0 as a critical point, and you have f of 0, 0 equals 0. Alright, so now since f of 0, 0 is equal to 0, then and this is lower than the minimum value, right? This is lower than the minimum value that was on the disk. So on D, so we may conclude that on D, f has a maximum of 2 and a minimum of 0. Okay, so remember, when finding the extreme values on a disk, always keep in mind, when finding the extreme values of on a domain, always find the extreme values inside the domain and the extreme values on the boundary of the domain, and then make a decision about what the extreme values are going to be. Okay, so this is the method that was taught in the previous lecture, of course. Okay, so the next topic is, of course, Lagrange multipliers with two constraints. If you have two constraints, what happens if you have two constraints? Let's look at the reasoning given. So suppose that we want to find the maximum and minimum values of function f of x, y, z subject to two constraints, right? G of x, y, z equals k and h of x, y, z equals c. Now these two are surfaces, right? And the maximum value, of course, of f, of course, is on the curve of intersection of these two surfaces. And if you recall, if f has an extreme value there, we know then both delta g and delta h are I mean, of course, delta g and delta h are both orthogonal to the surfaces g and h, and delta f is orthogonal to the surface f, right? So we know for a fact that the gradient vector is in the plane that's delta f is in the same plane as delta g and delta h, right? And which tells me that delta f is a linear combination of delta g and delta h. So we have to find the coefficients of the linear combination, right? So if we have two constraints, h x y z equals c1 and c2, and g x y z equals c1, if you have these two constraints, then you must have delta f equals lambda delta g plus mu delta h. Let me write this nicely. Lambda delta g plus mu delta h. So how many equations does this give you? Well, this gives us three equations. These are functions of x, y, and z, right? So two constraints plus three equations from three of these equations give us a total of 5 equations. These are two constraint equations. 3 equations from the fact that del f is a linear combination of del g and del h. So you've got 5 equations, right? And you have 5 variables: x, y, z, and lambda mu, right? And you could find these 5 variables using these 5 equations, and you'll get you'll get your maxima or your minima, right? So I want you to go through example 5, which asks you to find the maximum value of the function x plus 2y plus 3 on the curve of intersection of the plane x minus y plus z equals 1 and the cylinder x squared plus y squared equals 1. So you find the intersection, the curve of intersection of these two, and of course, I mean, you have these two constraints, and you want to find, and you want to set up these equations to find the maximum and minimum value, to find the maximum value of the function f. Okay, so you go through this example yourself, right? Please ask me during consultation if you're still confused. Okay, so in that case, I will see you on Monday, the 5th of April. Take care. I'll see you in